In video number 19 in the Foundations of the Computational Economics course, we are looking at the practical problem of measuring the volume of illegal trade with linear programming, and more specifically with the optimal transportation methods. The application comes from the paper titled Black Market Performance, Illegal Trade in Beijing License Plates. This is a very recent paper which was written by Øystein Daljord and co-authors. And I'm extremely saddened to say that Øystein unfortunately tragically passed away in June this year. He was a classmate of mine from Oslo and a good friend. And undoubtedly he was a very bright scholar. So the paper looks at the case of Beijing license plate regulations, and it measures the size of the black market, which was induced by the introduction of the regulation. So the idea is that if the lottery, which is the mechanism with of the regulation, so the license plates are assigned to the potential car owners by lottery. So if this lottery is run in the uniform random fashion, then the distribution of the purchased cars should not change. It is the number of cars that is purchased that would be changed, but the people selected in the lottery would represent the population of the people who bought the cars before, and therefore the distribution of purchased cars should remain pretty much the same. Well, in reality, there is a sizable shift in the distribution of cars, of new cars bought on the market. And the optimal transportation method is placed ideally to measure, what's the least of the shift of the probability mass in the change in distribution that was needed to observe the changes, or to explain the changes rather. So the background again is that in Beijing, to drive a car, a license plate from Beijing is required. But from January 2011, this license plate started to be rationed, and the quota was set to be quite restrictive, actually, the 35% of the previous year's sales. So the license plates are allocated with a lottery, which has a quite simple application, so it's easy to participate in. And in order to own a car, the potential owner, the household, they have to have won the lottery. Importantly, the license plates allocated by the lottery are not transferable, so it's illegal to sell the license plates. Yet there is a significant shift in the distribution of cars, and the shift is from the cheaper to more expensive car models. And this is hard to explain with the lottery, because, if the lottery was truly random, then all the same sorts of people who used to buy cars before would be still buying them. It would be just a smaller number of them. But the distribution wouldn't change. And the paper actually goes long ways in different robustness checks and different tests to establish that the black market is probably the most plausible explanation. So let's look at their main calculation and replicate that. What's the modeling framework? Well, denote with this the nicely written P with a knot, the distribution of car sales from the pre-lottery time, and P1 is the same distribution, the distribution of car sales in the post-lottery. The following assumptions are necessary. So the pricing policy, imagine that was the same, and that was the case. Demand structure didn't change together with the regulation policy, and that's quite plausible. And if the lottery is uniform, meaning that it's a uniform random distribution which is used to determine the winners of the lottery, then the distribution of the new car sales shouldn't change, right? Again, because the lottery would pick a smaller number, but from the same distribution, it would be a representative sample of the underlying distribution, and therefore the selected people who won the lottery would buy similar sorts of cars. The distribution of the new car sales shouldn't change at all. All right, so Oystein and co-authors were kind enough to share the data with us. Well, the main data. It doesn't include enough information to run all different checks, and the data is actually included with this this restricted data set is included with the slides. So let's look at the code. What do we need to do? We're going to be using pandas naturally. This is a stata data set, so we read stata. We use the method to read stata data sets directly. We will drop not missing observations right away, and this is done in place, as you can see. And let's just start looking at this data. So if I run this little code, we see that there is 243,000 observations. We have 3 variables. This is just the year of the sale, a month of the sale of a particular car, and we don't know anything about these cars. As I said, this is a restricted data set. But what we do have is this manufacturer suggested retail price. So we know whether this car is an expensive car or a less expensive car. So that's the data set. And let's look at the prices a little bit in more detail. So I'm just going to run the describe command here. And we can see that there are no missing values. Right, we deleted them. The mean price is 166. That's in 1,000 yuan. A large standard deviation. The minimum is 19. And some quantiles. Now look at the maximum. It's a car which is over 1 million. I think we would be doing ourselves a favor if we just delete the outliers on the upper tail, at least just for this exercise. This choice needs to be checked for robustness, of course, if that was a real paper. So what are we going to do? We can just calculate the quantile, the 99th quantile, using this command, Quantile command, in pandas. And then we say that the data is just gonna we're just gonna take the rows where the retail price is less than that calculated, and let's calculate a threshold, and let's describe the data again. Here we are. We've deleted what's about 2,000 observations. Could be a little bit on the high side. But let's go with this anyway. Now the maximum price is 600, so much less distant from the mean, and also the standard deviation expectedly went down. So let's call this data cleaning and work with this data. So then I'd like to see some histograms, right? The task here is to try to see whether there was any probability mass that had to move from the distribution of before the policy change to the distribution of the after the policy change. So let's draw some graphs. As we saw already in the previous videos, many times, standard commands to start using matplotlib. And let me show how this little function that I've written before was actually constructed. So I'll comment this out. We want a histogram, right? So let's find some good example. Matplotlib gallery histogram. What that brings us. As I was saying, the easiest way to learn Matplotlib is to look at the examples in the gallery. Let me just search for histograms. maybe just something simple like that. We can see that the command that we need is just called hist, and it takes the number of bins. But let's maybe look at the doc for the command itself. Doc hist, so that we don't miss any important arguments. Okay, so back to the code. I want to write plt hist, so I want to build histograms. Say we want the data. Well, we know what we want, right? The manufacturer suggested retail price, and we can access columns of the data sets with just the dot notation as well. Right, so bins, say 100. What else do I need to know? Well, let's try this. What's going on? We did get the histogram, but for some reason we also got the output. So here's our histogram. Well, you can see that this goes up to some thousands, and I actually want to draw the distribution, right? So how do I do that? Let's see, there's something called density here. If true, draw and return the probability density. Okay, I want density equals true. That's my next argument that I need to add. Now we're getting there. That's the density. Maybe this is too many bins. Well, maybe this is too few. Let's look at something like that. Now, because I want two histograms of two different data sets, I would look into the way to overlay a couple of histograms. And how do we do that? Look, there's this step type, hist type, and that I assume would be just the steps of the histogram, the outline. Yes, that's exactly what I want. Now these lines are easy to overlay from the two different data sets. And that's about it. So this is my command. Now I want to write a function, right, which would take the two different data sets and draw two histograms, one over on top of the other. 10, number of bins can be adjusted, and because there will be two histograms, I'll want to show the legend, and for that we need labels, right? And this basically explains my development strategy on how this function was written. So labels should be adjusted from the outside, right, from the caller of the function, and therefore we make them default, something like 1 and 2, and then they can be overwritten when the function is called. Okay, so this function will draw a couple of histograms, one on top of the other. All right, so let's see. We want to now draw two data sets, or two cuts of the data. Let me call this data 10 and data 11. And this will be filtered by the year. Data 10 and data 11. Maybe that's a little bit more clear what's going on. So we're taking the data that we already have. Now we are indexing the rows by making sure that the year is 2010, and we're taking the price, right, the MSRP price for both of them, and then we're giving these two data sets to the histogram function that we just looked at, and the couple of years. Something is not found. Apparently I didn't run this cell, and now we have it. All right, so the question here is, do we see a change in the distribution? And it could be a little bit hard to see, especially if we have too many bins. But too few of them, it's also may not be obvious. Although already with 5 bins, we can see that there's increase in this price, the cars which cost around 200,000. And it seems to be also carrying this increase into the more pricey cars. Now, does the picture change with the number of bins? Well, it does, but still you have this big peak around the 1000 car, which definitely goes down, right? And there are some increases over here. So there is some change that we see on this preliminary graphical analysis of the data. Okay, so the task is then to set up a transportation problem that could explain what is the minimum carry from the one distribution in blue here into the distribution in yellow that would be necessary to explain this change. Right. From the previous video, you probably remember that the transportation problem is set up in the following way. It's the minimization of costs. Xij is the amount of goods, while in our case, this is the probability mass that is carried from ith origin to j's destination. We want to minimize the costs, keeping the totals at origins and destinations correct, or in balance. Right, so the second line here, for example, it says that each origin j should leave in sum, the exact amount of goods, probability mass that it had. Right, now this, as you remember, is the optimal transport problem, which is not the same as linear programming. We have to convert it into a linear programming problem. In Python, there is a readily available solver for the linear programming problem, but not the optimal transport problem, although it wouldn't be hard to write. So let's look at the linear programming problem, which is solved by the SciPy optimized linprog. And if you look at the reference, and it's actually already open here, you can see that the solver knows how to convert the equality constraints and the bound constraints into the general form of ax less or equal to b. And therefore, we are able to give the equality constraints in the explicit form here. All right, so that's what we're going to do. Now, what do we have to do to convert the transport problem into the linear programming problem? Well, the x is a vector, and for us, an x is a matrix. So we need to stack all of the xij's into a single vector. And that, of course, also means that we need to stack the costs matrix into in a similar manner, and then prepare the A so that it works on the stacked vector. So express this equality constraints from the optimal transport problem using the matrix A, which works with the stacked vector of xij's. Okay, so this is going to be the first. This is going to be the first task to make. But let's also talk about, so what are we transporting? We're transporting the probability mass. And what are the origins and what are the destinations? Well, as you would think, the origin is the original distribution, and the destination is the resulting distribution. How do we index the origins and destinations? Let's talk about beans. Let's think about beans. So the first thing to do is to fix the number of beans that we will be working with. And I say n equals, say, 5. This is the number of bins to represent the distribution. Okay? The next task is to break the distribution of prices into this number of bins and somehow count how many observations we have in each of the bins. And that's going to give us the amount of mass, right, of probability mass that we want to, count and then convert it into the fractions. And that would give us the amount of the probability mass that we want to transport from one distribution to the other. Now, the way to do it is a pandas command called qcut. Let's look at that. It's Quantile-based discretization function. So what it does is that it takes a series or ND array or one DNA array and takes the number of quantiles that that it breaks the distribution into. Let's try that. So we want to say PD qcut PD qcut, and then we want to give it the data. And q equal n. And this is what it produces. Well, let's try to understand what that is. This is the representation of the object, and this is pandas core series. It's a series essentially, right? Okay, so it produces a series, and the series has this brackets as values, and these are the indices here. These are the indices. So instead of having brackets, it would be nice to have an integer saying in which bin this particular observation fell. Oh, and by the way, the number of observations here, I believe, is the same as the dt itself. So if we say printdt, yeah, that's the number of observations. Essentially, for each observation, the qcut command assigns this expression here that shows in which bin it fell. Now, if we read a little bit more, and I'm trying to change this into indices, so let's try to understand how to do that. Labels used as labels for the resulting bins. Oh, labels could be what we're looking for. Must be of the same length as the resulting bins. So if we give the labels to it, if false, returns only integer indicators of the bins. So, okay, that's what we should do. So we should say labels equals false. And there we are. So now A is what we get out of this qcut command is just the indicators or just integers, right? And I assume they're the indicators of the bins. So if we had more bins, then we had more of this. Okay, that's exactly what I want. And now that we know that this is an integer indicator, we can just put it inside of the data structure itself, inside of the data frame, and we can call this bin. Okay, now we want to calculate the fraction of observations in each of the bins. Okay, and how do we do that? Well, we can group by the name of the bin. So I would be writing something like group by, and then give it the name of the variable that I want to group it by. Okay. Now this creates the group by objects, and now if we apply the reduction command, like for example count, we want to count first. What are we going to count? Well, everything, right? Group by, I guess I have to say dp group by. There we are. And so here is the bin number, and we're counting all of the variables. Well, we can say we're counting mr p. I guess I should put it here like that. No. And of course this is misspelled. manufacturer suggested retail price, just like that. Okay. All right. So now we see that the bins that were assigned are from 0 to 4, and each bin has an exactly the same number of observations. Is this expected? Well, we were cutting by the quantiles, and of course quantiles are defined by having the same number of observations in each. But this is okay, right? Because we are representing the distribution of the prices in the whole data set. But now we want to group by and only look at the bins that correspond to the particular year. And this can be done with filtering the DT data set by saying year equals 2010, for example. How about now? Now the counts are different. Okay, now I want to do the same for the other year. So let me call this GR10, and let me copy this and say GR11. And print both of them. All right, so we can see that from year 10 to year 11, in bin 1 we have a reduction of counts or of the cars which fell into that category, and then what in here in bin 2 there's a reduction in bin 3, 32,000. It's also a reduction. Oh, we have a problem here as well, right? Because it seems that everything went down. Well, maybe there were just less cars sold in 2011. So we should convert this into the fractions rather than just counts. And let me call this fractions D10 and D11. Okay, and I take this. I want to divide by a scalar. The scalar saying how many cars were sold in year 2010, and that we can just find by counting in the original data set all the rows which correspond to year 2010. Okay, and the same thing can be done here for year 11. Okay, and now we can print T10, T11, just to check. And we get lots of nones. Let's see. So this is something unexpected is happening. So we know that these counts are by bins. Now this, I wonder whether this is a scalar at all. So let me say, okay, this is not a scalar, and that's because we are calculating the count for every variable. I want to restrict that to just one variable, say year. Now it's a scalar. Okay, so I can add this over here. Oh. And check again. And now we have a lot of output as well. So DT is now I'm printing DT rather than D. Okay, here we go. So D10 is the fractions of the distribution in year 2010 over the 5 bins. And we can verify that this sums up to 1, as it should. And now what about D11? And now we can compare, right? The fraction in bin 0 went down. The fraction in bin 1 went down. The fraction in bin 2 went down. The fraction in bin 3 went up. And the fraction in bin 4 went up significantly. And that's the change of in the distribution. So now these fractions can serve as the amounts of probability mass that we want to move from the origin to destination, the origin of course being D10 and the destination being D11. Okay, so let's start setting up a transportation problem. I import NumPy just in case. And let's think about the costs. So first, the costs should be such that it's free to leave the probability mass where it is in the bin where it already resides prior to the change in the policy. And it should be costly to move it anywhere else. So a simple specification for costs can be just a matrix with ones everywhere except for the diagonal, and the diagonal having 0. How do we do that? Well, we can take the NP ones and create the matrix in the size n by n, right, where n is the number of bins, and so that's the size of the problem. And subtract from this ones the matrix, the identity matrix, of also of the size n by n. Let's see what that is. And this is exactly the cost structure that I'm after. So, from any destination to, from any origin to any destination, it is costly to move the probability mass, but leaving it at place is costless. And by minimizing the cost of this transportation, we would be finding the bound. Now, which one? The lower bound, right? We will be finding the least amount of probability mass transfer that is needed to explain the change in the distribution. Okay, so these are the costs. The origins, let's just say that we want the convert the this data structure, the data frame into an array, NP array, and destinations is going to be an NP array of D11. Is this all that we need for the transportation problem? Yeah, that's about it. Let's just print all of them for checking. Separator of new line. Okay, so these are the origins and these are destinations, and we have everything set up with 5 bins. Of course, that can be easily changed to any number of bins, which is the flexibility of this code. All right, so the next step is to convert the transport problem into the linear programming problem, or rather, represent the transportation problem as a linear programming problem. And as you remember, we need to convert the matrix of costs into a vector, and similar, the variables will be a lone vector of variables that actually represent the xij's. So let's first convert the costs matrix, and so the way we will do it is we'll take costs and reshape it to the n by n, and this is going to be a one-dimensional vector of costs, and this will be C for the linear programming problem, right? So what I'm thinking about is this. So C is going to be just a reshape of the cost matrix. Now, how do we deal with the equality constraint? We need first to make sure that the sum of xi's for each origin, sum over the destination for each origin, is maintained. This is not particularly easy, but let me think about that. So So imagine that we are stacking the imagine that we are stacking this matrix of xi j column wise. It's actually not going to be important because of the symmetry of the cost matrix, but imagine that we're doing this. So instead of the matrix, we have this long column with x11 being the first one, the first element, and then xn1, and then x21, and so forth to, sorry, x, not 2, 1, but x1, 2 here, xn2, and so forth, the last being xnn. So we're stacking the xij's by column. Now, if we want to sum up this matrix in this direction, that means that we need to take the first element in each of the columns. So this will be spaced by n, and so forth. And so in the new A matrix that we are constructing for the linear programming problem, we want to have ones on these places that are spaced by n, right? And that should equal to the origin, you know, A1. And then in the second row, we would like to have one over here and one over here, and sort of diagonally many times. Well, this structure, when we have something that looks like a block repeated many times, in order to create this, what we need is a Kronecker product. And so let me write this here. So the first part of the A matrix, and I've written A1 here, is going to be a Kronecker product. It's going to be a Kronecker product of the ones vector, right? So this needs to be 1 by n, and we want to multiply that with an I matrix of size n. All right, just to check ourselves, let's plot a SPI of this A1. SPI is essentially just a simple plot that shows, let me go to the standard view here, that shows the non-zero elements of the array, right? So that's exactly what we wanted. This is the A matrix, and we have 25 columns. That's n by n is 5. And so the first column of A matrix has ones in the right places such that the origin equation is going to be satisfied. Right. The destinations are done exactly in the same manner, but now we want to cron the identity matrix with the vector of ones. And I hope this makes sense once we make the picture. Now, A, we want to vertically stack the A1 and A2. And let's make a SPI of A. Oh, there is an error. VStack takes one position argument by 2 of a given. And I suppose that just needs a tuple of the 2. Okay, here we are. So this is our A matrix. And the first row makes sure that, like I was drawing in the picture, the first row sums up to the correct A1. Finally, for the right-hand side, we just need to concatenate two vectors. It's not going to be VStack; it's just going to be concatenate. And what are the vectors? Well, they are origins and destinations. because the second half of the matrix will make sure that the destination equations budgets are also satisfied. Oh, and we have a problem here as well. What's the problem? Concat, probably. Okay. It was just misspelled. Okay, now we all set up to run the linear programmer solver. And so we are ready for the linear programming. Solver, let's import. What was that again? Let me look at the previous lecture. Optimize. And I'll just copy this whole block. So we are importing linprog. We can have this output, but now going back to the document here, so we need to give it C, the coefficients of the objective function, and so that's going to be C. Now AUB now have to be AEQ as far as I understand. Yes, and that's going to be A, and B also EQ. Equality constraints. It's going to be B. Simplic method is as good as always. And out. Okay, let's try to run this. It's going to give us a lot of output. And then it says also that, to my warning, AQ does not appear to be a full rank. What does it mean? So, because we have... So the way we constructed it, essentially what it means is that once n-1 equations are satisfied with the origins and destinations, then the last one is satisfied automatically, right? Because we are summing up across the columns and rows of the transportation model, and that corresponds to the rows of the A matrix to be sums of one another. So anyway, or the rows of A are linearly dependent. That's what it is. So a simple way to deal with that is actually just take one less row. So let's slice the matrix and go from the first until the next to last. Right, but we have to do the same with B then. And let's try doing that. There's a lot of output. Let's see, iteration 1, current solution is all zeros, and then it goes into trying different values. So let me actually delete the output here, and we don't need this function anymore. But let's get the result and print the result. Probably I don't need the spy A. Let me delete all of the other prints except for the result. So what do we have here? Here's the value of the function, and here's the x. To be able to see it, so res x, we want to reshape it back into the n by n matrix, and that will give us the transportation form of the optimal plan. And now what I want to do is look at the spy of x actually to see where the nonlinear elements are, and then probably also print x. And here we are. So the diagonal non-zero elements in X, they're fine, right? Because this is basically the probability mass which is transferred from the origin directly to from the origin bin to directly to the destination bin. which is the same bin. So this is where the two distributions are the same, but the off-diagonal positive or non-zero elements, this is where the interesting transitions happen. And we can see here that from the fourth, from the 0th bin, there is a transition into 4th bin. And here are the numbers. Here are the numbers. Right. And so what's the how do we calculate the amount of illegal trade? Like I said, everything on the diagonal is okay. This is where the probability mass did not transfer anywhere. So we can just write the lower bound on the fraction, on the share, let me say, of illegal trade is, and let's give it 5 digits after the comma. What is it then? We want to take x, and we want to take the diagonal of x, sum it up. Right. Well, actually, let's say, what's the sum of x, the whole x? Yeah, I didn't finish coding this. We can see it here, right? Because this is probability mass that we are transferring. These are shares or fractions of different distributions. Then the sum of x is always 1. So I can say that the estimate is 1 minus what's on the diagonal. Okay, and now this np diagonal x dot sum, that's going to sum up the diagonal of the x, which is fine. And now we can say that this is so. All right. And this is percentage of total trade. How do I print percentage? Like that, maybe? Yeah, okay. Let's multiply it by 100. What did we get here? I want to just multiply by the 100 this constant that we are printing. Okay, so here we are. So we've minimized the amount of transfer of probability mass from the distribution of before the policy change to the after the policy change using optimal transport problem, and we got this estimate of 16% of trade, which seems to be in a black market for license plates. Now the paper, if you remember, it got a different estimate. So they say that they estimate that at least 12% of the quota is illegally traded. Okay, so 12% and we're getting 16. Well, there are a lot of robustness checks. So for example, changing the number of bins may actually change the amount that we have here. It increased with 25 and stayed about the same. And if we have a large number of bins, then it takes some time to compute, and it's still working. Something is not right. So maybe the solver didn't actually solve. We need to check the responses here to be able to see what's going on. So staying with what a reasonable number of bins gives us an estimate of 18%. So, well, even though we're moving away from the result report in the paper, remember, we did make some assumptions and we cleaned the data in a quite drastic way. Maybe we can try and see how that affects the estimate. So, if I just take the 99, what is it, 0.1% of the sample. Yeah, then we've thrown out, what about 240,000, and here we have 241,000. Oh, it's almost 20. So just a couple of hundred observations. Let's see, and rerun the analysis. So I'm doing now what's called a robustness check. We're getting an error now. Oh, I'm not sure what's going on here. We are getting a 16% still. I assume that's because the data already has the bin calculus. I should have started from the very beginning and rerun all of the code. Oh, and now we're still getting about 16%. Well, maybe that's because of the nature of this restricted data set that is not exactly the same as in the paper. But anyway, that was our example. There is another version which I've written some time ago that you can also look at. But I believe it gives about the same result as we do now. Okay, see you next time.